Welcome back, I'm That Chemist, and today we're going to be ranking the most dangerous explosives. We will be categorizing them by their danger, stability, toxicity, as well as their synthesis. Before we get into the compounds for this tier list, let's first define what an explosive is. An explosive is any chemical compound, mixture, or device in which the primary or common purpose is to function by explosion. An explosion is the rapid expansion in volume of a given amount of matter, which is often associated with an extreme outward pressure release of energy, usually with the generation of high temperatures and the release of high-pressure gases. There are many types of explosive compounds. However, there are three main classes: Class A, Class B, and Class C, according to OSHA. Class A explosives are substances that possess detonating or otherwise maximum hazard capability. These include substances such as dynamite, picric acid, lead azide, and fulminated mercury. Class B explosives are compounds which possess a flammable hazard, such as a propellant explosive, which includes some smokeless propellants, photographic flash powders, and some special fireworks. Class C explosives refer to certain manufactured items like fireworks, safety fuses, detonators, and cartridges. These items contain either Class A or Class B explosives, or a combination of both, but only in restricted quantities. There are also 5 other important classifications of explosives, 2 of which are concerned with the detonation velocity, and the 3 remaining are concerned with the sensitivity of the explosive compound. For detonation velocity, there's low explosives and there's high explosives. Low explosives are substances where the rate of decomposition proceeds through the material at less than the speed of sound. These are known as subsonic explosives. High explosives are materials that undergo detonation, meaning that the explosive shock front travels through the material faster than the speed of sound. Substances with this capability are referred to as supersonic explosives. In terms of sensitivity of the compound, explosives can be sensitive to stimuli such as impact, friction, heat, static electricity, and electromagnetic radiation. Sensitivity of explosives can fall into one of 4 categories, which includes contact, primary, secondary, and tertiary explosives. Firstly, there's contact explosives. These are compounds that explode with very little stimuli. A popular example being nitrogen triiodide, which is so sensitive that it can be initiated with the touch of a feather or shifts in air currents. Up next, we have primary explosives. These compounds are extremely sensitive to stimuli, and some are even considered contact explosives. These are explosives found in detonators, percussion caps, and primers. Some examples of primary explosives include lead azide, nitroglycerin, and mercury 2 fulminate. In contrast with primary explosives, we have secondary explosives. These are the juggernauts of the explosive domain, since they have the perfect balance of stability and power. They're the undeniable kings of detonation. These include compounds such as TNT, also known as Trinitrotoluene, RDX, which is used in C4, and PETN, pentaerythritol tetranitrate, which is used in det cords. These compounds are less sensitive than primary explosives and require substantially more energy to be initiated, usually from a detonator. If you're not sure what detonators are, they're usually a tube made of metal or plastic that contains a small amount of a primary explosive. The explosive shock from the detonator is powerful enough to initiate the secondary explosive. Finally, we've come to tertiary explosives, also termed blasting agents. These compounds are incredibly resistant to shock to the extent that they cannot be reliably initiated using a detonator. Instead, they require an intermediate explosive booster, which is composed of a secondary explosive used to set off the tertiary explosive. Compounds such as ammonium nitrate and dynamite are 2 examples of tertiary explosives, which are extensively used in the mining industry. These explosives are usually much more affordable than secondary explosives, which is why they're widely used as blasting agents. Now that we have a bit of an understanding about the classification of explosives, we've chosen 15 compounds that we think are suitable contestants for this list. Keep in mind that all of these molecules are both illegal and very dangerous to synthesize and handle without a proper license and setup. Even F-tier molecules can cause severe damage if handled improperly. Let's talk about flavor. You know, that satisfying burst of taste that keeps us coming back for more. But what if I told you there was a way to indulge without the guilt? Enter FÜM, the flavored air device that's changing the game. Your mouth will enjoy the sweet taste of flavors like crisp mint and orange vanilla. It's like a tea party for your taste buds. And get this, FÜM isn't a vape. Nope, no vapor, no nicotine, just pure guilt-free flavor. Plus, check out its slick design. And here's the cherry on top. For a limited time, you can snag a free FÜM base by using code THATCHEMIST when you order the Journey Pack. It's the all-new magnetic stand for your FÜM device. It's a lot of fun to fidget with, especially if you're like me. Head to tryfum.com. That's tryfum.com and use code THATCHEMIST, or scan the QR code on screen to get your free FÜM base when you order your Journey Pack today. I want to thank FÜM for their support of this channel. Without further ado, let's get into the tier list. The first contestant is a compound that many of the hobby chemists might be familiar with. It's a popular choice for an energetic material due to the accessibility of the precursors as well as its straightforward synthesis. This compound is acetone peroxide. Acetone peroxide is also known as Apex and the mother of Satan due to its use in terrorist attacks, such as the Paris attacks on November 2015, which had resulted in 138 fatalities and had left 416 injured. The Belgium-Brussels airport incident in March 2016, which had resulted in 35 fatalities and 340 injuries, and the Manchester Arena attack in 2019, which had resulted in 23 fatalities as well as 1,017 injuries. These are just a few tragic examples of where acetone peroxide has been used for terrorism. Acetone peroxide was discovered by chance in 1895 by Richard Wolfenstein at the Technical University of Charlottenburg while investigating the oxidation of conene with hydrogen peroxide and acetone as a solvent. A bit later, in 1899 to 1890, two chemists, Adolphe von Baeyer and Victor Villiger, published several articles on the formation of the dimeric and trimeric forms of this compound. The dimer of acetone peroxide, DADP, has been reported to be more volatile but more thermally and impact stable than the trimer, TATP. Acetone peroxide has a peroxide linkage between each of the ketone units, forming a trimer or a dimer of peroxide ketals. This is a rather obscure motif in organic chemistry, but it's something that you come across from time to time. On the chemistry side of this compound, this organic peroxide is made by the acid-catalyzed reaction of acetone and hydrogen peroxide, but this isn't a reaction any of you should be doing. This compound at maximum density has a detonation velocity of 5,300 meters per second. Upon detonation, it releases 2,800 kilojoules per kilogram of energy. This is a high hypersonic, high explosive, since the velocity of detonation greatly exceeds the speed of sound. In terms of stability, it's highly unstable as an explosive. It can easily detonate upon impact with a hammer, and it has a very low auto-ignition temperature, ranging from 97 to 160 degrees Celsius.
You'll see it deflagrate rapidly the moment a flame touches it. Running a small amount will cause the TATP to deflagrate, then convert to detonation.
And that was just about 5 grams, not a lot of explosive. And yet this it literally warped this heavy-duty steel oil filter.
With this information, it could be considered a contact high explosive. One issue with this compound is its tendency to sublimate over time. This poses a significant concern, as it can lead to the decomposition of acetone peroxide crystals in areas that might be more susceptible to ignition or detonation. Aside from its uses in terrorism and amateur pyrotechnics, acetone peroxide has been used as a flour bleaching agent to bleach and mature flour. However, it's preferred to use safer alternatives, such as benzoyl peroxide. To wrap this up, whether it's the dimer or the trimer that's being prepared, this is an extremely unstable compound that should not be prepared by anyone without proper safety equipment, a license, and training. Assuming someone doesn't blow their fingers off preparing it, if caught manufacturing or possessing any forms of acetone peroxide, the law will treat this as a serious offense. You will serve time in prison for unauthorized production, ownership, or transportation of this chemical. With all these things considered, the accessibility of precursors, the ease of synthesis, the detonation velocity, and being the mother of Satan, this is going to have to go right into S tier. S for straight to jail. Gunpowder, also known as Blackpowder, stands as one of the earliest known pyrotechnic compositions. In 9th century China, alchemists were experimenting with potassium nitrate, sulfur, and honey. These early alchemists weren't trying to create a substance capable of destruction, but instead a substance which was able to grant immortality.
Why did they ever think of mixing these things together at this point?
The idea is to try to subdue the fiery properties of the sulfur and of the saltpeter so that they will be suitable for taking as a medicine, hopefully an elixir of life. We slightly move ourselves out of the immediate line of that, that's it.
Whoa! Okay. Wow.
That was quite striking.
Wow.
Yes. Well, as the Chinese alchemist said, don't try this at home.
In their pursuit of creating the elixir of life, alchemists had inadvertently stumbled upon gunpowder. As they experimented with various compositions, this mixture eventually gained recognition as one of the 4 great inventions of ancient China, alongside papermaking, printing, and the compass. The earliest known documentation of gunpowder was in a Chinese military manual called the Wujing Zhongyao, and this manual was compiled and edited under the direction of Emperor Renzhong of Song, who reigned from 1022 to 1063 during the Song dynasty. Wujing Zhongyao is translated as either collection of the most important military techniques or compendium of military arts. Over time, a standardized composition for gunpowder was developed, which consists of 75% potassium nitrate, 15% charcoal, and 10% sulfur. However, depending on its intended use, the ratio will vary slightly. In modern times, black powder has largely been replaced by smokeless powder, due to it being 3 times more powerful while producing cleaner combustion products. Smokeless powder is a propellant that's made with nitrocellulose, also known as gun cotton, and sometimes nitroglycerin, along with other additives for stability and performance. Unlike smokeless powder, the combustion of black powder emits corrosive, sulfurous fumes and a salty residue in weapons, eventually leading to the corrosion of vital components, which could render a weapon unusable. They are both classified as low explosives due to these compounds deflagrating rather than detonating.
Stand by for firing. Firing now.
Deflagration occurs when a substance burns at speeds lower than the speed of sound, while detonation involves a shock reaction with decomposition happening at speeds greater than the speed of sound. They're both considered to be Class B explosives since they're used as propellants rather than explosives. If a strong enough explosion occurs in a firearm, this will cause the weapon to rupture, rather than propel the projectile forward.
So when I pulled the trigger, the gun exploded almost immediately. So the first thing that went was this cap. The threads are sheared off of this gun completely.
An explosion results from these substances being ignited in a confined space. The rapidly expanding gases build up pressure within the container, and when this pressure suddenly impacts the air molecules surrounding it, a rapid pressure wave or shock wave is generated, which we perceive as an explosion. This is similar to dry ice in a bottle. When the sudden pressure rise occurs, the bottle suddenly expands outward, causing the bottle to rupture and creating a really loud bang. These compounds have seen many wars, and a lot of lives have been lost ever since the creation of these compounds, and they continue to claim lives every single day. Considering its extensive use in warfare and the legal restrictions surrounding its manufacture and ownership without a license, as well as its inefficiency compared to other explosives, I think we can put black powder right into F tier. If you don't know what flash powder is, back in the 19th century, early photographers used a device called a flash stand. This device was held overhead, and with the aid of an electric igniter, the flash powder was ignited, producing an intense flash of light. This intense flash of light was used to illuminate a roll of film in a box camera. The ignition of flash powder produces a blindingly bright flash, which leaves traces in your vision. This is referred to as an afterimage. In modern times, flash powder is mainly used in fireworks and flashbangs. It's usually composed of a metal powder as a fuel and a salt as an oxidizer. Reactive metals such as aluminum, magnesium, magnesium, and titanium are used. In terms of oxidizers, potassium chlorate, perchlorate, nitrate, permanganate, and dichromate are often used. Depending on the application, different mixtures can be prepared, favoring a fast or slow burn rate. On a note of safety, one very dangerous property of flash powder is its ability to self-confine or pack down very tightly. This can cause it to explosively burn in air when initiated. Something that should be avoided in chlorate-based flash powders is the use of additives such as sulfur and antimony trisulfide. This will reduce the ignition temperature as well as sensitize the mixture to impact and friction. Sulfur can also react with metals such as magnesium and aluminum to form metal sulfides. These metal sulfides can react with atmospheric moisture to produce hydrogen sulfide, which is an extremely toxic gas that reeks of rotten eggs. With all that said, it's not a good idea to reproduce this. Flash powder is extremely powerful, so powerful that even 1 gram is enough to do some serious damage. It's much more powerful than gunpowder, and it should be handled with greater respect, but ideally, it shouldn't be handled at all. Even preparing metal powders for flash powders is dangerous, as finely divided metal powders can self-ignite upon contact with the air.
This is what happens when you ball mill and you go too long without opening the container. As I was dumping the contents out, the aluminum powder went supernova on me, and it was extremely dangerous because it did flash and it kind of flared my eyes a little bit. Not bad, but let's go look at the ball mill. Okay, well here's my ball mill. The media had a hard time coming out of the end, and when I turned it upside down, I kind of had to give it a little shake, and I bet what happened, I incorporated just enough oxygen in the wrong spot, and it caused it to go. And it just looked like a hot ember had fallen into it. Once you see that little ember in it, you only have seconds, and the whole thing's going up. There's nothing you can do about it. You can't stir to put it out. It would be a huge disaster if you tried that. You're just going to create a big flashbang, and you can hurt yourself. So please use precautions anytime you're ball milling. I used some, and it was still dangerous. So,
Despite its power, it's still considered a Class B low explosive, as it does not exceed the speed of sound when it's initiated. Flash powder, I think we can put this into A tier. It's a simple composition, but things can go wrong. However, if you really want to work with this stuff, you can visit the Pyrotechnics Guild International, PGI, or the National Fireworks Association, where you can find more information on acquiring a license and training concerning this composition. HMTD, also known as hexamethylene triperoxide diamine, is a high explosive organic peroxide. It's a heterocyclic compound with a cage-like structure. This molecule essentially looks like two trimethylamine molecules got into a street fight, and now they're both handcuffed to each other, 3 times. It was first synthesized in 1885 by the German chemist Ludwig Legler by the acid-catalyzed rearrangement of hexamine and hydrogen peroxide. The velocity of detonation for this compound is around 5,100 meters per second at maximum density, making it a Class A high hypersonic explosive, since the velocity of detonation exceeds the speed of sound. It also releases 5,612 kilojoules per kilogram of energy when initiated, making it even more energetic than acetone peroxide. HMTD also has a very high friction sensitivity, as well as a high shock sensitivity, which would classify it as a primary contact explosive. Due to its ease of synthesis similar to acetone peroxide, it's been used in terrorist attacks. One incident is in the 2016 New York and New Jersey attack. Fortunately, this incident didn't result in any fatalities, but sadly, 34 injuries occurred. In most countries, it's illegal to manufacture or possess any quantities of HMTD. No one should be making this since it's illegal, and in general, organic peroxides are very unstable compounds that you really don't want to be messing around with. So HMTD, it's been used for terrorism, it's extremely unstable and can explode very easily. This compound can go right into S tier. Acetylene has the chemical formula C2H2. It's the simplest alkyne that exists. Acetylene is a colorless, highly flammable gas which consists of 2 carbon atoms triple bonded together with a hydrogen on either side. Due to the triple bond, acetylene is highly reactive and energetic, making it useful in various industrial applications, such as welding, cutting, and chemical synthesis. It's typically produced in the lab by the reaction of calcium carbide and water, and industrially, it's produced by the partial combustion of hydrocarbons. Acetylene also plays a critical role in many industries, such as metal fabrication, chemical manufacturing, and pharmaceuticals. Despite its use in many industries, acetylene is a highly explosive gas. When exposed to air or oxygen, acetylene can undergo rapid combustion, which releases a significant amount of energy in the form of heat and light. This combustion reaction is highly exothermic, which means that it generates a large amount of heat as a result of the reaction. In my time as an undergrad, one of the professors decided to fill a few balloons with oxyacetylene, where the oxygen was in excess so that complete combustion occurred. Previously, they had used an excess of acetylene, but this led to the formation of soot. Covering the whole class in soot when this detonation occurred was something that the students weren't a fan of. So instead, he decided to use an excess of oxygen. However, because this was done, it ended up resulting in a very loud shockwave that ruptured my eardrums and left me physically and emotional damage. The explosion had gone off with such a tremendous bang that it literally ruptured my eardrums. All I heard was "ee." I didn't even hear the bang because it was so loud and so fast that it ripped my eardrums before they even had a chance to register what had just occurred.
Wow. I can't hear. That's the first time I've ever had my ear.
I said it was going to be loud.
That's the first time I've ever had my ears ring.
I think we're going to have to... My ears are ringing. I have tinnitus. So this is tinnitus.
This is why you probably shouldn't be handling explosives, because if a chemistry professor at a university didn't know what he was doing, you probably don't know what you're doing either. Interestingly, acetylene has an explosion limit of 2.5 to 82%. That's a very scary range, as this means that 2.5 to 82% acetylene in air will explode if an ignition source is present. Yikes! Another scary fact about acetylene is that if it's stored under pressure exceeding 30 psi, it will become shock sensitive. To mitigate this concern, acetylene tanks are halfway filled with a porous material soaked in acetone. If I had to rank this, it would probably go into D tier. Under normal circumstances, it's not an explosive, but it does easily form explosive mixtures in air. I think it's pretty fair that we put it in D tier because the teacher who did this was a total D for doing this. Mercury fulminate is a primary explosive that is highly sensitive to heat, friction, and shock.
Oh yeah, my ears are ringing like crazy right now.
This compound was first prepared by Edward Charles Howard in 1800. It was prepared by dissolving mercury in nitric acid and adding ethanol to the solution. I was unable to find an exact reaction pathway for the preparation and decomposition of this compound. However, it might be as follows. In the past, mercury 2 fulminate has been widely used as a trigger for other explosives in percussive caps and detonators. However, in modern times, it's been replaced by more efficient compounds, such as lead azide, lead stiffnate, and tetrazine derivatives. Mercury fulminate has a low decomposition temperature, even as low as 100 degrees Celsius. This property of mercury fulminate was exploited by the Soviets during the war in Afghanistan, where they were trying to suppress the Mujahideen. For better food, they would barter with local merchants. They had traded bullets for a proper meal. However, prior to trading the bullets, they would boil the bullets in a pot of water for about 4 to 5 hours. This would decompose the mercury fulminate primer in it, which would render the bullets useless. I've linked an excellent video on this topic in the video description, covered by the channel Infographics Show. Nowadays, however, this will not work, as bullets use primers that are more thermally stable than mercury fulminate. Mercury fulminate has a detonation velocity of 4,250 meters per second. This makes it a hypersonic explosive. Considering its instability and power, this will fall into the category of being a Class A primary explosive. Since the production of this compound deals with highly soluble mercury nitrate, its decomposition products are either mercury oxide or mercury vapor, and it's a very unstable explosive. With that said, I think we can put this compound into B tier. B for boiled in water. Nitroglycerin is a dense, colorless, oily, explosive liquid that is produced by the nitration of glycerol with white fuming nitric acid under appropriate conditions to form the tris nitrate ester. This compound is an organic nitrate rather than a nitro compound. However, the traditional name has been retained. It was first made in 1847 by Ascanio Sobrero, and it has been used as an active ingredient in the manufacture of explosives, namely dynamite. This is a formulation that Alfred Nobel was able to figure out. That's right, the same Alfred Nobel who's responsible for the Nobel Prize. It probably wouldn't surprise you that it's been employed in construction, demolition, and the mining industry. It's also been used in warfare, such as in World War I and II. Nitroglycerin can also be combined with nitrocellulose to form double-based smokeless powder, which has been used as a propellant in artillery and firearms since the 1880s. In addition, nitroglycerin has been used for over 130 years in medicine as a potent vasodilator to treat heart conditions such as angina pectoris and chronic heart failure. As an explosive, it has a detonation velocity of about 7,700 meters per second, which makes it a high hypersonic explosive. This, in combination with a specific explosive energy density of 1,488 calories per gram, makes nitroglycerin 49% more energetic on a mass basis than the standard definitional value assigned to TNT, precisely 1 kilocalorie per gram. With all that said, nitroglycerin is a Class A primary high explosive, which we can place right into S tier. S for Sobrero. Picatinny liquid explosive, PLX, is a liquid binary explosive. It's a mixture of 95% nitromethane along with 5% ethylene diamine, which is used as a sensitizer. Nitromethane on its own is an explosive. However, it's so insensitive to shock that it cannot be detonated under normal circumstances without a sensitizer. Despite its simple composition, PLX is a powerful high explosive, marginally exceeding the destructive yield of TNT. During World War II, the Picatinny Arsenal in New Jersey invented a composition with the specific purpose of clearing minefields. It could be dispersed from the air or poured from a safe distance and detonated by ground troops. It was the supposed explosive used in the film Die Hard. However, the film had greatly exaggerated the sensitivity of this mixture, as it still needs a detonator in order to detonate.
This stuff is cutting edge. It's a binary liquid.
A what?
Either one by itself, you got nothing. But mix them.
Charlie, you're gonna be wearing that shirt!
Mike, Charlie! Like I said, very cool stuff.
PLX has a detonation velocity of about 6 to 7,000 meters per second. It's still a relatively stable explosive once mixed. However, the components are a bit difficult to acquire, and PLX is also a very powerful high explosive, which exceeds the destructive yield of TNT.
This is nitromethane, ethylene diamine. They both start almost clear, but as I add a small amount of this to here, you'll see that it becomes a bright yellow. This is now a sensitized high explosive. Done. Triply sensitized. Now you might think, oh, be careful. However, sensitivity is a relative thing. I'm going to show you what I mean by sensitized. Just a couple drops.
This is nitromethane and diethylene triamine. They're two liquids, so you literally take the cap off of one atom, pour it in here, and it instantly arms. We'll put a blasting cap to it.
Due to its stability, even when the two components are mixed, this would be a Class A secondary high explosive, as it still needs to be initiated using a detonator. With that being said, I think we can put PLX into D tier. D for detonator. TNT, more specifically 2,4,6-trinitrotoluene, is a chemical compound that was first prepared in 1863 by the German chemist Julius Wilbrand. Industrially, it's prepared in a three-step process. First, toluene is nitrated with a mixture of sulfuric and nitric acid to produce mononitrotoluene, MNT. MNT is separated and then nitrated once more to produce 2,4-dinitrotoluene. And in the final step, the dinitrotoluene is nitrated to trinitrotoluene using white fuming nitric acid and oleum. After nitration, TNT is stabilized by a process called sulfitation, where the crude TNT is treated with aqueous sodium sulfite. This removes the less stable isomers of TNT and the other undesired reaction products. Initially, TNT was originally used as a dye, and it took them 28 years before they realized its explosive properties. These properties were discovered in 1891 by a German chemist, Karl Hausemann. This compound is so insensitive that it needs to be initiated using a detonator along with an explosive booster. It has a high detonation velocity of 6,900 meters per second, making it a high hypersonic explosive. With that said, we can say TNT is a Class A secondary high explosive. This compound is also one of the most widely used explosives in various fields, such as in the military and mining. It's so extensively used that most explosions, both nuclear and non-nuclear, are compared to TNT. For example, the Trinity test of the Manhattan Project, which was the first detonation of a nuclear weapon called the Gadget. This device exploded with an energy equivalent to 20 kilotons of TNT. And the Tsar Bomba, a 50 to 58 megaton nuke that was tested in the Soviet Union. If you think these numbers just sound like numbers, the Beirut explosion, which happened on the 4th of August 2020, has been estimated to be an explosion equivalent to 1.1 kilotons of TNT. Keep in mind that 1 megaton is 1,000 kilotons, which goes to show how insanely powerful these nuclear weapons truly are. And that's with only a fraction of the nuclear material even being consumed. So yeah, nukes are terrifying, in case you didn't already know that. TNT equivalent is a convention typically used to describe the energy released in an explosion. A ton of TNT is a unit of energy defined by convention to be 4.184 gigajoules, or 1 gigacalorie. This is the approximate energy released in the detonation of a metric ton or 1,000 kilograms of TNT. The kiloton is a unit of energy equivalent to 4.184 terajoules of energy. And the megaton is a unit of energy equal to 4.184 petajoules of energy. In other ways, for non-nuclear explosives, it's expressed as the relative effectiveness factor, or RE factor. This relates to an explosive's demolition power to that of TNT, in units of TNT equivalent per kilogram. The RE factor is the relative mass of TNT to which the explosive is equivalent. The greater the RE, the more powerful the explosive. For example, nitroglycerin has an RE factor of 1.54, which means that 1 gram of nitroglycerin is equivalent to 1.54 grams of TNT. With that said, TNT is a useful compound, and it's stable enough to be stored. Since most explosives are compared to that of TNT, I think we can put TNT right into C tier. C for compare this to other compounds. RDX is an abbreviation of Research Department Explosive or Royal Demolition Explosive. Another name for it is Hexogen, or 1,3,5-trinitro-135-triazine. It's an explosive compound that was discovered by George Friedrich Heinig in Germany, and it was patented in 1898. Chemically, it's classified as a nitroamine, and it's a more energetic explosive than TNT. RDX was widely used in World War II and remains a common explosive in military applications. It's often used in mixtures with other explosives, plasticizers, or phlegmatizers, which are also referred to as desensitizers. This compound is also the main explosive in C4 and is a key ingredient in Semtex. It's stable in storage, and it's considered to have some of the highest brisance and is also one of the most energetic of the military high explosives, with a relative effectiveness factor of 1.6. This means that 1 gram of RDX is equivalent to 1.6 grams of TNT. In a laboratory setting, it can be prepared by treating hexamine with white fuming nitric acid, as shown in the pathway below. Modern syntheses employ hexahydrotriacyltriazine as it avoids formation of HMX. During World War II, the US produced about 15,000 tons per month, while Germany had produced about 7,100 tons per month. RDX had the major advantages of possessing greater explosive force than TNT in World War I, and it required no additional raw materials for its manufacture. Its synthesis is relatively simple, it's a highly effective explosive, the usage of it in common plastic explosives such as Semtex and C4 makes it highly useful for military applications. Aside from its use as an explosive, it also has been used as a rodenticide. Explosive-wise, this would be considered a Class A secondary high explosive due to its stability and destructive power. With that said, I think we can put this compound into B tier. B for brisance. HMX, also called Octogen or 1357-tetranitro-1357-tetrazocane, is a very powerful and relatively insensitive nitroamine that is chemically related to RDX. The compound's name is subject of much speculation, having been variously listed as high melting explosive, high velocity military explosive, or high molecular weight RDX. Unlike other explosives, HMX is more complicated to manufacture, and this confines it to specialist applications. HMX is produced by the Bachmann process, which is the nitration of hexamine using a mixture of ammonium nitrate and nitric acid, in a mixture of acetic acid and acetic anhydride as the solvent. It was first made in 1930 by Werner Emanuel Bachmann in the United States. In 1949, it was discovered that HMX can be prepared by the nitrolysis of RDX. HMX is almost exclusively used in military applications, including detonators for nuclear weapons, in the form of a polymer-based explosive. Another use for it is as an additive in solid rocket propellant, such as when it was used in the Peacekeeper, an intercontinental ballistic missile. HMX has a low sensitivity to both shock and friction. It also has an extremely high detonation velocity of 9,100 meters per second, the highest of all compounds on this list. This detonation velocity is so high that it falls into a category of velocities known as re-entry speeds. This is the speed that would be reached by objects re-entering Earth's atmosphere, such as asteroids. Due to its stability and power, it can be classified as a Class A secondary high explosive. For that reason, I think we can put this compound into S tier. S for supersonic. Gotta go fast! Ammonium nitrate is a chemical compound with the formula NH4NO3. It's a white crystalline salt consisting of an ammonium cation and a nitrate anion. This compound was first made in 1659 by the German chemist Johann Rudolf Glaube. Despite this compound being discovered quite early, its explosive properties were first put to use in World War I. Ammonium nitrate in some form has been used as a fertilizer for much longer. This compound is industrially made from the products of two processes: the Haber-Bosch process, which combines nitrogen and hydrogen over an iron catalyst to produce ammonia, and the Ostwald process, which produces nitric acid by reacting ammonia and oxygen to produce nitrogen dioxide. This produces nitric acid when it reacts with water. Ammonia and nitric acid then react to form ammonium nitrate, due to ammonia being a base and nitric acid being an acid. This reaction produces the salt ammonium nitrate, which is predominantly used in agriculture as a high nitrogen fertilizer. Its nitrogen content is really high, at 34.5%. However, many countries are phasing out its use in consumer applications due to concerns over its potential for misuse and terrorism. To render it safe for retail, however, it's often mixed with calcium nitrate and is sold at fertilizer stores as calcium ammonium nitrate. There are also safety concerns when working with ammonium nitrate on an industrial scale. Accidental ammonium nitrate explosions have killed thousands since the early 20th century. One recent example of a disaster was the Beirut explosion, which happened on the 4th of August 2020. This had resulted in 218 fatalities and over 7,000 injuries. It had also caused $15 billion in property damage, and it had left 300,000 people homeless.
Oh my god!
This isn't the only disaster, but there have been multiple incidents where ammonium nitrate has caused destruction to property and livelihood. I've linked a list of ammonium nitrate related disasters in the video description. When ammonium nitrate is heated above 300 degrees Celsius, it breaks down to form nitrous oxide and water, as shown here. The thermal decomposition of this compound can sometimes be explosive, so if you're thinking, that's an easy way to produce nitrous oxide, you might want to reconsider it. Aside from accidental disasters, ammonium nitrate has been used in terrorism, such as in the 1995 Oklahoma incident, which had resulted in 168 fatalities and around 680 to over 720 injuries. Aside from its application in agriculture, the explosive properties of ammonium nitrate are exploited in mining. Where it's used as a cheap and relatively stable blasting agent. In terms of stability, ammonium nitrate still requires either a tremendous amount of heat or a blasting cap and explosive booster in order for it to explode. It also has a very low sensitivity to shock and friction, making it a safer alternative to other compounds for blasting. Ammonium nitrate also has a fair detonation velocity of 2,500 meters per second, making this a supersonic explosive. Due to its stability and power, it can be classified as a Class A tertiary high explosive. One thing to note is that there are also mixtures of ammonium nitrate with fuel oil, nitromethane, aluminum powder, and many other compositions that are used to increase the overall effectiveness of this explosive. So ammonium nitrate, it's used in agriculture, as many of our foods are still dependent on this compound. It's still a danger in its pure form, but as an explosive, it requires either a very powerful shock or intensive heating to set it off. With that said, as an explosive, I think we can put this one into F tier. F for fuel oil. Picric acid, also known as 2,4,6-trinitrophenol, is a strongly nitrated organic compound that has been used in many wars, such as the Battle of Omdurman, the Russo-Japanese War, and World War I. It's made by the sulfonylation of phenol or acetyl salicylic acid using sulfuric acid, which yields 5-sulfonyl salicylic acid. This is followed by nitration using nitric acid to yield 2-nitrophenol 4-sulfonic acid. It's then nitrated twice more to produce 2,4,6-trinitrophenol. During the reaction, it puffs out a ton of nitrogen dioxide gas, which is very dangerous, and it should be avoided in general as it's still illegal in most countries to synthesize this chemical. The first person to synthesize picric acid was Peter Wolf in 1771. Picric acid serves multiple purposes beyond its explosive properties. It's employed as a biological stain, an antiseptic, and it's used to test for creatine in blood samples. Additionally, a 4% picric acid etch known as picral is used to reveal prior austenite grain boundaries in ferritic steels in optical metallography. Historically, picric acids and picrate salts quite often got used in organic chemistry. Because picric acid is a pretty good acid, you could have a picrate as a fairly unreactive anion. The problem is, people start doing melting point analysis on salts containing a picrate, and what happens when you heat up a picrate? Foomp! So we don't use picrites as much in synthetic chemistry anymore. The same would also be true for perchlorates. Despite its uses, picric acid is still sensitive to heat, shock, and friction. When the crystals of picric acid contain less than 10% water, it becomes a potent explosive, with a detonation velocity of 7,350 meters per second. Even when moistened, it remains classified as a flammable material. Having such a high detonation velocity makes this a high hypersonic explosive, and due to its sensitivity, it can be considered a Class A primary explosive. Picric acid, like most acids, will also react with metals and bases, such as copper, lead carbonate, and ammonia, to form picrate salts. Ammonium picrate, also known as explosive D or dunite, was a picrate salt that was extensively used by the US military for aerial shells in World War I. If I had to rank this, it's not as bad as some of the other ones on this list. Its synthesis is relatively easy, but also dangerous, and with that said, I think we can put this into D tier. D for dunite. Dun-dun-dun-dun-dun, nite. Our penultimate pair of compounds is PETN and ETN. These compounds are quite similar. PETN is an abbreviation for pentaerythritol tetranitrate, while ETN is erythritol tetranitrate. When PETN is mixed with a plasticizer, PETN forms a plastic explosive. It's one of the main ingredients in Semtex, C4, and det cords. Penta refers to the 5 carbon atoms of the neopentane skeleton. It's the nitrate ester of pentaerythritol, and it's structurally very similar to nitroglycerin. Interestingly, like nitroglycerin, PETN and ETN are also vasodilators. As such, they can be used for certain heart conditions, such as for the management of angina. However, ingesting these compounds or having prolonged skin contact can lead to absorption, resulting in a nitro headache. These compounds are similarly made by the reaction of either pentaerythritol or erythritol with concentrated nitric acid. One quality that ETN has that PETN does not is a positive oxygen balance, which means that ETN possesses more than enough oxygen in its structure to fully oxidize all of the carbon and hydrogen upon detonation. For every 2 moles of ETN that decompose, 1 free mole of diatomic oxygen is released. This oxygen could be used to oxidize an added metal powder, or it can be added to an oxygen-deficient explosive, thus boosting the overall power, i.e. bigger boom. In terms of sensitivity, the impact and friction sensitivity of ETN is slightly higher than the sensitivity of pentaerythritol tetranitrate. PETN and ETN are very powerful explosives, with PETN having a relative effectiveness factor of 1.66 and ETN having an RE factor of 1.60. They both have very high detonation velocities, with PETN being 8,400 meters per second and ETN being 8,200 meters per second, making them both high hypersonic explosives. To sum these up, these are both Class A secondary explosives with a lot of destructive power. Therefore, we can put both of these compounds into S tier, S for Semtex. Lastly, we have azides. And if you put azides down the drain and you have any lead pipes, it might be the last explosive on your list as well. In chemistry, an azide is a linear polyatomic anion with the formula N3-. It's the conjugate base of hydrozoic acid HN3. Organic azides are organic compounds with a formula RN3. These are compounds which contain the azide functional group. Organic azides also play a central role in click chemistry, a type of reaction that led to the 2022 Nobel Prize, where copper-1 catalyzes an azide-alkyne cycloaddition reaction. This forms products known as triazoles, and these play an important role in research and medicinal chemistry broadly speaking. One of the cool things about this reaction is, in a biological context, you don't normally have azides, and it's pretty rare that you have alkynes. So you can set up a way to image cells such that you have the only 2 building blocks that you need, an alkyne and an azide. Those can click together in the cell, and you can suddenly visualize stuff. Pretty cool, hey? These reactions are known for their high efficiency and selectivity, and they've found broad applications across many domains. One dominant application of azides is as a propellant in airbags, specifically sodium azide. In an airbag, sodium azide breaks down to produce nitrogen gas, which inflates the airbag, protecting the occupants of the vehicle from sudden impact. Sodium and potassium azide can be used in an aqueous solution to prepare salts of insoluble azides such as lead, silver, and copper azide, which were commonly used in primers and blasting caps historically. Almost all azides are primary explosives due to their sensitivity, with the most sensitive one being azetoazide azide, an extremely cursed 2-carbon, 14 nitrogen-containing compound. However, according to Tom from Explosions and Fire, it's not as sensitive as Hank Green from SciShow claims it is.
This compound has a reputation as being mankind's greatest explosive.
Azetoazide azide, the most explosive chemical compound ever created.
I've made the tetraazide, I've made the azidyl. The first time that the sensitivity is not through the roof. Okay, don't get me wrong, it's sensitive as dicks, you know, like this is really sensitive. But is it the most sensitive explosive ever created? No. I can name 2, maybe 3 explosives that I've made personally that are more sensitive than this compound. Exposure to flame will cause fire. Exposure to flame for the tetraazide causes some instant detonation with some tremendous power. You can actually melt before they detonate.
It's still, however, incredibly sensitive, but nowhere near the sensitivity of nitrogen triiodide. In general, azides are highly reactive compounds which are known for their explosiveness due to the presence of the azide functional group, which can rapidly release nitrogen upon decomposition. This instability makes them dangerous to handle, requiring strict safety precautions to prevent accidental detonations. Azides are a class of compounds which tend to be as toxic as cyanides. They have a similar mechanism of toxicity, inhibiting mitochondrial cytochrome C oxidase and catalase. This leads to a disruption in the electron transport chain, resulting in cytochrome C oxidase inhibition and nitric oxide generation, which likely underlie the hypotension, myocardial and respiratory failure, and metabolic acidosis that occur in azide poisoning. With that said, it's an extremely toxic group of compounds. They're sensitive to heat, shock, and friction, so there's no other place for azides aside from A tier. A for azide. In this video, we've delved into various explosive compounds, However, I want to finally emphasize one last time the importance of safety. If you're considering making explosives at home, please reconsider. Not only are you putting yourself in danger, but you're also risking the safety of those around you. Beyond the knowledge shared here, I hope that you'll walk away with a greater respect and understanding of these compounds. Thanks for watching, and I hope you have a great day. Thanks again to FÜM for sponsoring this video.